Okay, so today is cycle 11, second meeting. And I just wanted to take a moment to tell you guys, right, the last time I saw you, we took our assessment. So once you get your feedback on that, you'll have a 2-week window to reassess. So be patient with that. I'll plan to give that back to you guys next week so that you have it. So over Wednesday, when we were doing the asynchronous lesson, some of you guys did as I asked, which I appreciated. You were introduced to our new standard of thermodynamics, and you also went through an introductory little thought experiment about heat. So based off of that, I created y'all's bell work for today, which, as you can see from our agenda, we'll do a recap of that, and then we're going to go into some new content still relating to heat and thermodynamics, but this thing called calorimetry. So let's go ahead and start with our bell work. So on y'all's in the bell work, you guys do not have this table up here at the top that gives you specific heat. So just make sure you are utilizing this on the slide. So with this, based on your thought experiment, we should have discovered that to calculate heat, we use this equation. You got mass, specific heat capacity, and the change in temperature to find heat, which if we don't remember that right now, I'm going to recap it in a second to make sure we know what we're talking about. Okay, so in our problem, and I always like to list things out. Okay, we have a 27.6 gram sample that has a temperature of 25.3 degrees Celsius. So this would be your initial temperature. And it's heated to a final temperature of 101.3. So there's our final temp. What is the amount of heat present in the system? So we are looking for Q. Okay, the change in temperature. Remember, when you calculate that, you always want to take final minus initial. So for this, it'll be your 101.3 minus 25.3. Okay, you can do that off to the side. You don't have to write it out. So that should get us to 76 degrees Celsius as our change in temperature. And then this guy, our specific heat value, you just get from a chart. If I don't give it to you in the actual question, I'll have you just go find it. So for this one, I forgot to specify who it was. So I just wanted to pick gold. So we'll use that specific heat capacity. So the 0.128 joules per degree Celsius gram. Okay, so our next step is just plugging in. And in this case, right, using our equation, we do not have to rearrange, which is nice. So I'm just going to plug in my numbers as I have them. Okay, and your last step, right, no rearranging, so all you have to do is plug in your values, and you should get, and remember the unit for heat, that Q is joules, which is just that capital J. Right, so don't worry about sig figs or anything, just get your number, double check your work. Right, and on to the next, so I want to kind of focus in on what we're doing today based off the standard. So with our thermodynamics, our level 2 stuff, we're going to recap the heat, energy, temperature, and specific heat, which is what you should have gotten out of that thoughts experiment video. And we're also going to discuss the law of conservation of energy, very similar, right, to the law of conservation of mass. And then we'll bring in these two new terms, exo and endothermic. Some of you guys may already know what they mean, which is great. And then we'll actually apply them today with the calorimetry. So the level 3 stuff we're going to focus on. Utilize equations to calculate heat, specific heat, mass, final temperature, or the change in temperature. So this one, we really use that Q is equal to MC delta T, change in temperature. So we've kind of done that briefly and then explained differences between your heat and temperature. Really, I just want you to know, or I want you to be able to articulate to me that we do know heat and temperature are two different things and that they're not the same, which is something that is actually a misconception a lot of the times. And then today, our big focus with the new notes that we'll be taking is calculating energy lost or gained with calorimetry. And while we do that, we'll kind of talk through the process of how that works in a lab setting. And this is something that you guys will actually do when we're in class together. So go ahead, you'll need your lab notebook, something to take notes on, right? Pencil, paper, and we'll get started. So the recap of our thought experiment, I want to make sure we're all on the same page, right? So our heat energy is the amount or quantity of hotness, okay, which is different from our temperature because temperature is the degree of hotness. And you can also kind of define it in terms of how fast particles are moving. Right, the faster particles move, the more or the higher the temperature will go. So the next one, our specific heat. So this is the amount of energy required for a 1 gram sample to increase by 1 degree Celsius. So that specific heat value, that's why you see the unit that you do. So the unit is joules per grams degrees Celsius. And that's what it means. It's saying that I need this amount of energy to get 1 gram up 1 degree Celsius. So something kind of interesting to notice is that water has one of the higher specific heat capacities, which means it actually takes a decent amount of energy to heat it up. So if you've ever boiled water, now you kind of know why it takes forever or seems to take forever when you're boiling water. Okay, and then the last thing, I just want to make sure that equation Q is equal to MC delta T, right? Heat is represented by Q, specific heat is the little c, mass I hope we recognize, and then of course our change in temperature is delta T. Okay, so that's just a recap to get our minds back in focus. We're going to be using that equation Q is equal to MC delta T with our calorimetry as well. So calorimetry is a process, so it's referring to actually what we would be doing kind of in the lab. So it's a process to measure and exchange of energy in a system. So what you can see off to the side, this is a calorimeter. It's a very simplistic one. There are ones that, of course, are more fancy, but you can achieve this protected, right, isolated system with our heat with some styrofoam cups. So you guys will actually, this will be the setup that you guys use in the lab Very simple, like I said, you just have your thermometer, you've got your stir, you've got the metal, and you've got water. So there's going to be a transfer of energy from metal to water. So when we do this in lab, we're going to heat up the metal as hot as we can get it. So probably about 100 degrees Celsius. And we're going to transfer it into that water that would be at room temperature. Okay, so at that point, what we're going to have is this heat exchange, right? This transfer of energy from metal to the water, because the metal has more heat stored because of the temperature that we're seeing, the higher temperature, and it's going to exchange with the water. So as part of this, one of the things that we utilize when we're trying to apply a calculation when it comes to heat exchange is understanding that law of conservation of energy. Okay, so law of conservation of mass, right? Mass can neither be created nor destroyed with a physical or chemical change in an isolated or a closed system. So, right, very similar here as well. Energy cannot be created nor destroyed. It only transferred to an object or a different form of energy, right? So you can have, this is probably something you guys have been taught, especially with like potential and kinetic energy. You have that stored energy, it then becomes that kinetic energy, which could then turn back into that stored energy, that potential energy. So it never really goes away, right? It just goes into a different form. Same concept with the law of conservation of mass when you guys did all those labs, right? Usually if we saw some sort of loss or gain, there was some sort of error on our part in the way that we did our lab work, right? And a lot of the times with the stretching of the steel wool, some people will stretch it, you know, off to the side and all that stuff falls off. So it's still there, we just didn't keep it in our system. All right, so taking this kind of concept of the law of conservation of energy, we utilize and can actually in the lab look at the change in temperature of our system using that calorimeter. Okay, so what we can do is, since we know our metal is going to transfer that heat to water. So the reason why we put the negative is because we know it's going to lose heat, and the water is positive because we know this guy is going to gain. Okay, so from that, we know that for heat, we can calculate the heat using our equation that we discovered through our thought experiments, and we can plug that in. So on this side, this still represents the metal, okay, and then on this side, we've got our water. Okay, so same stuff, this is still mass, right? This is still your change in temperature, so the final minus initial, and then this is your specific heat value that you are going to be getting from a table or a chart, right? Or it'll be outright stated in the problem that I give you guys. So you'll notice a lot of this is really about algebra, and applying those skills. So we're going to go through an example together utilizing this specific equation. So that's where we're going next, which is why I put the standard back up here for us. So what we just did is utilize this equation, and now we're going to apply it in order to calculate using calorimetry. So in these problems, the best thing that you can do for yourself is list out everything, okay? Because you have mass, specific heat, and change in temperature for the metal as well as water. So I always just label off to the side, and I use the little m to represent for metal, and then of course W is for water. Okay, so in our example, we have a 25-gram piece of iron, right? So that's important because we're going to need to get our specific heat value. At 124.85 degrees Celsius. Now that's not the change in temperature, right? So that is actually your initial temperature of the metal, okay, and it's placed in a styrofoam coffee cup, so our fancy calorimeter, containing 25 milliliters of water at 24.85 degrees Celsius. So again, we are given an initial temperature, and this is specific to the water. So assuming that no heat is lost to the cup or the surroundings, so we're assuming that the law of conservation of energy is occurring and that we have that closed system, what will the final temperature of the system be? So we're not trying to find the change in temperature. We're actually looking for the final temperature. Okay, so that means we're really going to have to use our algebra skills. So we want final temperature. So I'm going to just write our initial temperature here. Okay, and then the mass of the water. Now, if you guys remember, the density of water is 1 gram per milliliter. So we're saying 1 gram of water equals 1 milliliter of water. So since I have 25 milliliters, I know based on the density that it's equivalent to 25 grams. Okay, our specific heat of water, you just run over to your chart, 4.184. Okay, again, those are always given to you. You do not have to memorize them. All right, and then we have final and initial. So because we know that negative Q of the metal is equal to Q of the water, their final temperature, they're going to meet an equilibrium. Okay, so their final temperature is going to be the same. So I say that because algebraically that's going to come in handy when you combine like terms. Okay, so the equation that we are using just like from before, okay, our metal and our water. So I'm going to go ahead and start plugging some things in. Oh, sorry, this is 124. I wrote that down wrong. All right, so we've got all this stuff, and now it's really just about applying those algebra skills that you guys have and doing what you can. Okay, so I know from here that I can at least do this math out in front. So I'll go ahead and get my numbers for that. And remember, keep this negative with you. Otherwise, some stuff might get messed up. Now, as we keep going, we're still just doing algebra. So the next easy step would be to distribute out into the parentheses. So we'll go ahead and do that. Don't forget about your negative for this side. All right, so the next thing that you would have to do before you move on, okay, is deal with this negative. So you go ahead and same thing, you're going to distribute out. So if we still know our algebra, once I do that, I now have this negative here, and this is my plus. So this goes away because we distributed it. Okay, and so now, again, it's just about combining your like terms, doing some more algebra. So I'm going to go ahead and move this guy over. Right, so I'm going to add it to this side so that it'll cancel out here. Okay, and if you guys want to, you can do both sides of this all at the same time. That's kind of you and your skills. All right, so next thing that we got to do, right, we have to move the other guy over. So you would add right, and you might notice this is the longest version of these types of problems as when you're being asked to solve for the final temperature of that system. Okay, so on this side, all right, so the very, very last thing that we would have to do, right, you're trying to solve for the final temperature. So again, just algebra. You want to divide both sides by your 93.375. And then I'm going to find some space somewhere. I'll put it over here. To get our final temperature. We got 42.846 degrees Celsius. And of course, please double check my math, right? If that doesn't seem right based off what you got, just let me know. I may have just made a calculation error on my part. Okay, so again, this is the longest type of problem that you guys will see. Otherwise, it might be something that you get all the information and I want to know what the mass of the metal is, right? So it's not as long as drawn out because you're not going to be doing any distributing. Just makes it a little easier. And in that case, you could actually move, right, these variables to the other side and plug in all your numbers just at once and you get your final answer.